Hello and welcome to this video on proof by induction. In this video we're looking at a series sum. Now throughout this video series we'll be looking at different types of proof by induction, but for all the types the process of proof is the same. There are 4 steps. Step 1 is the base case, where we prove the general statement is true for n equals 1. Step 2 is called the assumption, where we assume that the general statement is true for n equals k. Step 3, which is the one where we actually have to do some work, is called the inductive step, and we show that the general statement is then true for n equals k plus 1. And as a result of doing all that, we then can conclude in our 4th step that the general statement is then true for all positive integers n. It's a bit like having a sort of series of dominoes, where if you topple the first one, the n equals 1, 1, and then the rest will follow. So the example we're going to look at, we're going to show that the sum from r equals 1 to n of 12r minus 8 is given by the expression 2n times 3n minus 1 for all natural numbers n, so r 1, 2, 3, 4, 5, etc. So starting with the base case, that's when we show that it's true for n equals 1. If we substitute n equals 1 into the left-hand side, that's the sum of the first 1 term, i.e. the first term. That's when r is 1. 12 times 1 minus 8 is equal to 4. On the right-hand side, when we substitute 1 into that to get the series sum, we have 2 times 1 times 3 times 1 minus 1, which is the same as 2 times 2, which also equals 4. Hence, we've shown that the left-hand side and right-hand side are the same. So the summation is true at least for n equals 1. It's now our job to show it's true for other values. So our next step is the assumption, and all we're literally doing there is we're assuming that the summation is therefore true for n equals k. So we're just rewriting the expression with k's instead of n's. So 2k times 3k minus 1. That's just to bring a different variable into it. So at this point, it's probably a good idea just to ask, what does success look like? How will we know that we've actually got the right answer? So what we're aiming to obtain is the summation expression, the same one, but with n equals k plus 1 rather than k. And that's why we're using k rather than n, because we're looking for something slightly different. So where we had 2n, 3n minus 1 before, if we substitute n as k plus 1, we get 2 lots of k plus 1 multiplied by 3 lots of k plus 1 minus 1. And then if we simplify that, we get the expression 6k squared plus 10k plus 4. If we achieve that when we're looking at the k plus 1 sum, then we know that we've achieved our goal. So next we look at the inductive step. That's the step where we have to do some work. And here it is. So when n equals k plus 1, what we're saying is that if we run the series sum from 1 to k plus 1 instead of just k, then that is the original sum from 1 to k, plus this extra term with the k plus 1 in it. So we've substituted k plus 1 into 12r minus 8. So the first bit with the sigma, that is the original series sum from 1 to k, but then we're also adding on the extra term, the k plus 1th term. We can then replace our sigma, our 1 to k for 12r minus 8, with the thing that we've assumed in the second step, which is that it equals 2k lots of 3k minus 1, and then also add to that our k plus 1th term. And if we expand the brackets and simplify it, we get 6k squared plus 10k plus 4, which is indeed what we said success would look like on the previous slide. So hence, our answer is true when n equals k plus 1. So it was true for the number 1, for n equals 1. We've now shown that if it's true for k, then it's true for k plus 1. That means that if it's true for 1, then it's true for 2. If it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4, and so on to infinity. So we finish off with the conclusion. And the conclusion says that since it's true for n equals 1, and since if it is true for n equals k, then it's also true for n equals k plus 1, it is therefore true for all n. And that's the end. Thank you very much.